So I'm from Melbourne, Australia. Took me a very long time to get here, but I thought it'd be fun to come across the other side of the world and come to a conference and talk to you guys about some hacker shit and have fun, drink beers, etc. So I'm the principal consultant at Assurance, a pen testing company in Melbourne. Yeah, we basically do typical security consulting stuff, pen testing, security review, bit of architecture, not a great deal of policy and boring shit. This was a longer presentation that I've cut down, so I've got way too many slides, so I'll have to breeze through it pretty quickly. Yeah, and I don't have any lolcats. Yes. So what I'm going to talk about is firmware-based rootkits on Macs. I've seen quite a few Mac laptops around the place. Seems to be pretty prevalent in InfoSec these days, and obviously execs who want their shiny toys. So I'm going to go through a little bit of introduction about the goals that I set out to achieve with this research. A little bit about EFI fundamentals, how it works, and what sort of aspects we can attack, how to do some bad things with it, how we can gain persistence for our rootkit, and a few boring slides about defensive measures. So first off, the reason that I initially started doing this stuff was that I wanted to have a cool boot screen on my Mac that came up before the kernel, right? And as soon as I dug down into how EFI works, I went, well, obviously there's some more bad stuff that can be done with this. So I looked a bit further into it, and of course, it's all been done before. So there's been quite a bit of other work in this kind of area, particularly with BIOS-related stuff, with old MBR viruses. All those guys have talked about some similar stuff, so definitely worth checking out all that as well if you're interested. So the basic goals that I set out to achieve were to be able to backdoor a machine preferably without any evidence on disk, and to be able to persist forever across reboots, across reinstalls of the operating system, if possible across actually replacing the hard disk. So yeah. And then for our rootkit to be able to batch the kernel at boot time and mess with stuff at a pretty low level, and to work regardless of whole disk encryption. So it was pretty tricky because I didn't really know a lot about firmware, didn't really know anything about BIOS level stuff. So it's a lot of fun. So some fundamentals about how EFI works. It's basically I'm sure you guys have all heard about UEFI at this point. It's a BIOS replacement. It was written by Intel quite a few years back by a dude called Andrew Fish, who actually now works at Apple. It was called the Intel Boot Initiative, and it was basically designed to overcome some of the problems with the legacy PC BIOS, some of the limitations, and depending on who you ask, it does and doesn't solve some of those problems. It's used on all modern Mac hardware, and it's also used on a whole lot of modern PC hardware under the name UEFI. And there's a compatibility support module which basically emulates the legacy PC BIOS. So you may have it on a motherboard and not even know that it's there because it looks like a normal BIOS when it boots. A little bit of terminology there. UEFI, after version 1.10, was handed over to an open source community group called the Unified EFI Consortium, and they've managed its development from then on, but it's pretty much been the same guys involved in the development of it. So Apple's version is actually pretty old, reports as version 1.10, though they've done some quite extensive customizations and built new drivers for it and stuff. So one of the key things about EFI, the E in EFI stands for extensible, the extensible firmware interface. So it's designed to be modular and to be able to be added onto fairly easily without any dodgy low-level kind of development, and with a standard development kit that works across all versions. Yeah. So it's made up of a set of core components that reside on the firmware flash on the logic board, on the motherboard. A set of applications like the shell, telnet client, an FTP client, a whole bunch of shit. Some drivers for supporting hardware like PCI buses and Ethernet interfaces and all that sort of stuff in the pre-boot environment. And then OS loaders. So as I said, the core components reside on the firmware flash on the logic board. Typically, some applications like maybe the EDK shell, not on Macs but on VMware, resides on the virtual firmware flash. Along with a set of drivers to basically initialize the system. So Drivers can also reside on disk on the EFI system partition, which is a 200 meg partition at the start of the disk if you're using the GUID partition table, or on option ROMs or expansion ROMs on PCI devices, which is a lot of fun as well. So developing for EFI is really easy because it's all in C. So there's no no assembly mode, assembly hacking basically to write stuff for EFI. You can depending on what you want to do, but to build a basic driver for EFI, it's all in C. It builds PE executables, uses the FAT file system, so it's all building on old technologies and making stuff pretty accessible. So part of the EFI development kit is Tiano Core, which is Intel's reference implementation. So EFI is a specification, it's not a product. And Intel has implemented the specification and called it Tiano Core. It's open source, and that's pretty much what most BIOS vendors actually use in their implementations, the majority of their implementation. If you have a look at the EDK, there's actually around about 2 million lines of code in .c and .h files. I didn't do a very scientific analysis of that. I just WC'd all the files. But it's nearly twice the size of the Mac OS X kernel. So it gives you a pretty good idea. There's quite a lot of source code in there, and it hasn't really been audited. The spec's like 2,200 pages long, specifying all the protocols and the internals of EFI. It's pretty huge. And just some telling examples of the protocols that are actually specified in the UEFI specification. Like it has IPsec support, it has a full network stack, it has crypto stuff, it has like stuff for drawing forms, and like it's an entire operating system in your firmware. So onto the fun stuff, actually doing some bad things with it. So, as I said before, it's quite extensible and modular, which makes it really easy to build additional drivers for EFI. So, what we can do is we can build a rogue driver. We can get loaded fairly early on in the boot process. We can register some legitimate callbacks that are specified as part of the UEFI spec. We can hook, do some dodgy shimming on various boot services and runtime services. So boot services are functionality provided by EFI in the pre-boot environment, and then runtime services are functionality that's provided by the EFI framework for use in the pre-boot environment and in the OS present environment. So the OS can actually call back into EFI to do stuff like, convert VM addresses from physical to virtual and stuff like that. So yeah, it's pretty easy to actually develop for. So one of the cool things we can do is attack whole disk encryption. I thought this was probably, something that'd be pretty cool to have a mess around with. So File Vault on the Mac basically has the disk looks like this. There's 3 partitions. There's the EFI system partition, the encrypted OS partition, and then at the end of the disk there's the recovery partition. So when you hold down Command R at boot time and you boot up into the recovery partition, you can reinstall your operating system or whatever. So when the machine boots with this scenario, the platform firmware initializes, the bootloader is loaded from the recovery partition because the main OS partition is encrypted. The bootloader prompts the user for their passphrase, uses that passphrase to decrypt the AES key off the disk, and then the AES key is used to unlock the disk and decrypt the rest of the system and continue booting. So we can actually pretty easily interfere with that process. Basically just install a keystroke logger within EFI. So we hook into the simple text input protocol, which is just the console, well, it's a generic protocol that's used for console input within the pre-boot environment. Specifically the instance that's actually installed by the bootloader for that cute little, password entry screen. So we just replace a pointer in that protocol that points to the read keystroke function with our own function, typical function hooking, with a table. So every time the key gets pressed, that gets called, we get called, we store the keystroke, call the normal function. Everyone's happy. So another way we can attack whole disk encryption is actually stealing the AES key. I haven't actually tried this, but I thought it would be worth mentioning because I don't think it would be too difficult to do. We could hook the load image protocol, which is the load image function, which is part of boot services, which is what's called by various aspects of EFI to load binary images from option ROMs, from disk, from firmware, whatever, load them into memory and be able to execute them. So we can mess with that and wait until the bootloader gets loaded and just patch the bootloader to do whatever the hell we want. And fortunately, IDA Pro actually understands EFI binaries quite well because they're PE and it's x86 binary. So IDA Pro actually just assembles these quite nicely, and Apple's left us some pretty debug logging there that's quite helpful in figuring out how their bootloader works and various other aspects of their firmware. So the next, probably the most fun thing we can do here is actually patch the kernel. So what can we actually do from EFI? Well, we can get execution before the kernel is loaded, and we can wait around until it gets loaded, and then we can patch it and let it continue on. So we just need to find a place within the kernel image that gets loaded into memory to put some shellcode, not really shellcode, but a payload, hook some kernel functionality, point it to that payload, so we get execution during kernel initialization, and then it's all awesome. The one problem is that, it's not really a problem, but the initial problem I came across was that the kernel isn't loaded but when we get loaded. So what we've actually got to do is wait around until exit boot services gets called by the firmware, and then we can mess with the kernel. So we have a quick look at the boot process here. So we've got the standard platform like EFI initialization stages. So the sec phase establishes a root of trust for the system. PEI sort of initializes most of the chipsets, the CPU, memory, I think. Then DXE phase actually loads drivers from firmware, from option ROMs, from disk, whatever. And then we actually, so we load our driver. So this is where our driver gets loaded. Following that is the BDS phase, which is the actually the boot, like the disk select screen that when you hold down the option key when you boot a Mac, you get that screen to choose what your boot target's going to be. That's the BDS phase. So the BDS phase actually scans all the partitions on available disks, looking for bootloaders. Well, looks at the file system header to find blessed partitions, finds the bootloader, loads it up, continues on booting. So the bootloader gets executed with whatever arguments you've given it. Then it loads the kernel off disk. Or the kernel cache, depending on what the boot process is going to be for this instance. Then it prepares the environment for kernel execution. So preparing the environment involves like setting up a virtual memory map that the kernel can use, cleaning up after all of the drivers that have been loaded, and destroying all of the stuff that was in the pre-boot environment that's not used once the OS is running. So one of the important things that it does is it calls exit boot services, which tells all of the drivers that have registered for an exit boot services callback that they need to clean up their memory, mark anything as runtime services data that they're going to need later on, and unload themselves. And then the kernel is executed. So we actually get a pretty good opportunity there to get execution when the kernel's been loaded, and we can touch it up. So in order to actually mess with the kernel image in memory, we need to know where it is. It's actually pretty easy to find out because we can just look at the Marco header of the kernel binary itself and see that the first load command there specifies a virtual memory address of 200,000 hex in the upper canonical half of memory, which is where the kernel image itself is loaded when the machine is booted. So on a running system, if we point GDB at VMware or using KDP at the running system and just have a look at that memory address, if we look at the 4 bytes there, we can see that it's the Marco magic number feed face, or feed faces for the 32-bit, that's the 64-bit version. So that's where the kernel starts. So if we look at this in the 32-bit memory map that EFI uses, because it uses a 32-bit memory map without paging, we pretty much just truncate the address and it's at that 200,000 hex address. So that's pretty easy. So what do we actually do in order to Trojan the kernel? We need to inject a payload somewhere, as I said, patch a kernel function somewhere during the early initialization phases of the kernel and point it at the payload. Probably using a trampoline sort of payload to load a bigger second stage, because we don't have a lot of options as far as where we're going to put our first stage payload within the kernel image. So we can actually load a second stage payload from like an EFI variable, which is what I'm going to use, or previously allocated runtime services memory, or potentially over the network, lots of other options. One that John Heisman suggested was also, splitting up your payload over multiple PCI option ROMs and that sort of thing. Plenty of options. So in this example, or in the demonstration that I'll show you, I'm basically just sticking the payload in the page alignment padding at the end of the text segment of the kernel. So all the kernel segments are loaded on page boundaries, which is pretty standard. On the default 10.7.3 kernel, we actually get almost an entire page, which is pretty cool. So we wouldn't really necessarily need to use a second stage payload because we've got a huge amount of memory to play with there. Huge in the context of a fairly stealthy rootkit payload. So yeah, that's pretty sweet. So we've been called by exit boot services. We know where we can store a payload. We know how much memory we have to store it. So what do we actually put there, and how do we get it called? So nearly halfway through. All right. So how do we get it called? I'm going to answer the second question first because it makes more sense that way, trust me. So we're going to patch a function in the kernel's boot process. I actually use load init program. I thought that was a pretty good candidate because it's, by this stage, most of the kernel subsystems have been initialized. We've got a full memory map. Everything's pretty good because we're about to actually execute the init process and continue loading the rest of the system. So what we do is we save the first instruction in the function, or the first 8 bytes or 4 bytes or whatever, depending on how much memory we need to patch. I think we need 5 bytes to do a relative jump, so I save the first 8 bytes of the function. Override it with a relative jump back to our payload, which is stored at the end of the text segment in the page alignment padding. So what is our payload? It's as I said, like a trampoline payload that loads a second stage payload. So the trampoline payload is basically going to save the state of the processor because we got called by an inline patch, like an inline jump. So we need for the kernel initialization to continue and the machine to boot afterwards. So we need to save the state of the registers, find where our next stage payload is in memory. In this case, I've stored it in an EFI variable, which is stored in the NVRAM, 64K data flash on the board. That's used to store like the boot device and initial screen resolution and stuff like that. So then we call the next stage payload's initialization, let it set itself up, install its tentacles all through the kernel and whatever rootkit hooks it's going to use. Restore the patched instruction that we used to jump to our first stage payload. Restore the state of the CPU. And jump back to load init program and let the kernel continue initializing and boot as normal. So there's a diagram of basically what I just said. Hopefully that makes sense. Yep. More beer. So what do we do once we're actually in the kernel? I'm not going to talk a whole lot about this because I don't have I've got 11 minutes left. So I've talked about kernel rootkits on macOS previously, so there's a whole bunch of stuff. It's actually not on my blog, but I'll put it up there if you're interested in actual kernel rootkit techniques on macOS. And another dude, Fractal, who's a Portuguese dude who's done some very cool research as well. So we can do all the typical kernel rootkit stuff that you can do on a BSD kernel or a Linux kernel or Windows or whatever. So we can hook syscalls, we can install network kernel extension callbacks, so we can get called on socket syscalls on packets incoming and outgoing at the interface level and at the IP stack level. We can install trusted BSD policy handlers to get called when MARC syscalls are called. We can patch whatever the hell we want. There's lots more stuff. So what I'm going to use in my example is basically just hooking the kill syscall. So we just overwrite an entry in the sysint table with a pointer to our own kill wrapper that checks for a special condition, whether the magic signal number has been specified, and then continues on and calls kill as normal, potentially elevating the requested process to root or whatever, which is what I do. So I'm going to demo that in a minute, but first I'm just going to talk a little bit about persistence, because that's pretty key to rootkits. So there's a few options for persistence of EFI rootkits. In ascending order of awesome, we can patch or replace the bootloader on disk. We can use the EFI system partition to store a driver. We can use a PCI device expansion ROM, or we can actually write to the firmware flash. So looking at each of those in a bit of detail, not a whole lot of detail. So messing with the bootloader, if we're writing stuff to the disk, particularly to the system partition or the recovery partition where people are going to be looking, we might as well just patch the kernel or install a kernel extension or some other typical kernel rootkit technique. It is somewhat useful for evil mate attacks because even with file vault turned on, the bootloader is actually stored, as I said, on the recovery partition, which is in clear text. So yeah, we can mess with that, but I give it a 4 out of 10. It's not that great. The EFI system partition, I actually thought this was not used at all because that's what I've read previously, but with a little bit of experimentation and a chat to Alex Ionescu, who's the author of Windows Internals and a world-crushing badass, he told me that drivers are actually loaded from the extras directory, which is contrary to the spec on the system partition. So that's kind of useful. It's also used to stage firmware updates on Macs. But yeah, overall, it's on disk. It's not that great. So expansion ROMs are pretty cool. Graphics cards in my iMac, most MacBook Pros have an expansion ROM used to store the driver that's used by the graphics card in the pre-boot environment. So we can overwrite that. We might mess with the graphics in the pre-boot environment. We can fix that. We can just patch that driver, or do lots of other things. VMware's like virtual Ethernet interfaces actually have option ROMs, which is really helpful for testing, and is how I'm going to do one of my demonstrations. And we can write to most of these firmware flash, expansion ROM data flashes from the operating system because they're all on the PCI bus. So yeah, did a bit of reversing on one of the graphics firmware updates for my iMac and figured out how to do that. And you can actually do it with FlashROM, which is a tool provided by the Coreboot dudes for flashing BIOSes, so that's quite useful. But yeah, it's actually pretty awesome because we can store on an option ROM, and if we pull the disk out and put a new disk in, it's still there on the option ROM. Firmware flash is, I guess, the ultimate goal. It's kind of hardware specific, not as hardware specific as option ROMs because it's always going to be there, so it's not necessarily not going to be on some machine. And if we did write to the firmware flash, we can actually modify everything about the firmware. We can Trojan all of the early phases and really mess with things if we wanted to. And again, typically we can write to the firmware flash from the OS. I think on newer machines, they actually use the write protect pin on the data flash correctly, and you can't. But you could do it from the early EFI phases if you've got code execution early in the EFI boot process, which is what some of the dudes at Invisible Things Lab did in one of their demonstrations talking about UEFI a couple of years ago at Black Hat. So all in all, that's a pretty badass technique because we can really, really backdoor a machine. One other problem with this is that Apple's boot ROM actually checks the signature on the firmware flash. So there's a few other things you've got to work around to do this, and I actually bricked my test machine doing that. So I need to desolder the firmware flash and flash it with my bus pirate. We'll see how that turns out. A little bit more about firmware flash. The actual format of the firmware flash file system and firmware volumes is all specified as not as part of the EFI spec, but as supplementary documents to the EFI spec, so it's all documented there for you really nicely. I'm not going to talk through too much of this stuff because I've only got a couple of minutes left. There's a few tools that people have written for manipulating UEFI capsules and firmware volumes, but they're typically aimed at slick BIOS mods and stuff like that, so they're not really good for actually replacing or adding drivers to volumes, so I had to write my own stuff. But as I said, it's all specified, so it's not really that difficult because you just got to follow the spec. And yeah, as I said before, the binaries are PE, so actually disassembling Apple's firmware, not very hard. So there's the output of my tool. Awesome. So I'm going to do a couple of quick demos in the few minutes that I have left. I'm going to demonstrate a really simple proof of concept EFI rootkit called Defile. I'll demonstrate loading it in two ways. So the first is an evil maid type attack, loading it from a USB flash disk. So we basically just plug in the flash disk, boot off it, sort of, to run a custom bootloader which loads the rootkit driver into memory. So it registers a callback for exit boot services. Exit boot services gets called. It stores its main payload in an EFI variable. All the stuff I said before. Patches the kernel, grabs the second stage payload, and installs the rootkit hooks. The payload hooks the kill sys call, and we can call the kill sys call with our magic number from the userland and get root. So the second way that I'll demonstrate is exactly the same as that, except I'll load it from a virtual expansion ROM using VMware. Yeah, so I'll do that now. Demo. So I need two hands to do this, but I'm just going to boot the virtual machine, drop into the pre-boot menu, pass through the, oh, thanks man. Yeah, pass through the USB flash drive to the VM and choose that as the boot target. So VMware really sucks at this and sometimes doesn't let me do it. So, yep, okay, so this is the this is VMware's version of the pre-boot menu, which is all graphical on the Macs. So I'm just going to pass through the flash drive, which is already done. Good. Drop into the boot manager here. So this is the equivalent of holding down the option key and booting off a USB drive. So there's my custom bootloader and achieving my initial goal of actually getting a cute boot screen before the kernel loads. My friend drew that because he's a legend. So now we just let the kernel boot as normal. That was that quickly flashed up there was the actual output, debug output, thanks Louis, of the driver doing its thing and messing with the kernel. Now the kernel will continue booting, hopefully, and we'll see what happens. There's last week's attempt. So if we hit up our little rootkit command line here, we should get a shell. And there we go, root shell. Huzzah. Okay? So I'll demonstrate another way to do this quickly. It's not a very good demonstration because it's using VMware, but I really want to bring another machine that has an option ROM in it. So what I'm going to do is I'm going to specify within the VMware configuration file just like an option ROM to use for the Ethernet interface. So now when we boot the virtual machine, I know you didn't see that, but it's not really that relevant. So now when we boot the virtual machine, we should see the patch output just come up sort of automatically, maybe. So that's EFI initialization, there we go. So it's patched the kernel. So the EFI driver has been loaded from the DXE phase of EFI from the virtual option ROM on the Ethernet interface, and then it's loaded the driver, which is registered at the exit boot services callback, patched the kernel, etc. So on a real machine, we might have stored that in the graphics card option ROM. And I'll just try that thing again, see what happens. Root shell? Yeah. All right. So that's my demonstration. And everything is fine and nothing is ruined. I'm almost out of time, so I'll breeze through the defense stuff because it's boring anyway. There's a few options you can take, a few measures you can take to prevent these kinds of attacks. EFI firmware password actually kind of sucks. It's definitely worth setting. If you don't have one set, definitely set it, because it prevents things like FireWire DMA attacks, and it will prevent the type of evil mate attack that I demonstrated with the USB flash drive. It will not prevent attacks against the firmware flash or option ROMs or anything like that. But it is a good preventative measure to take against evil mate attacks. And there are actually quite a few ways to remove it. So if your machine is out of your hands for more than a couple of minutes, and you think something's fishy is going on, someone could have actually just killed your EFI password by popping a couple of RAM chips out and resetting the parameter RAM. UEFI secure boot is something that's definitely worth taking note of. It's part of the UEFI specification. I won't go too deeply into it. If you want to read about it, it's kind of interesting. It's basically a process of signing drivers and other components within EFI to ensure that they come from a trusted vendor. And this is something that the Linux community has kind of been up in arms about recently, because it's introduced the possibility of OEMs being able to actually lock out end users from being able to run Linux on their machines because they have to run a trusted bootloader, which is, Microsoft's bootloader, right? It has a few issues. It's basically, according to the specification, the NVRAM has to be tamper-proof. It's not tamper-proof in current machines, so they would actually need to do some hardware changes, probably to really make it useful. If the drivers in the kernel actually aren't signed, then you could pretty much just set up a whole fake EFI environment and continue booting from there, and load your EFI rootkit from there. So it's not great, but I think Apple actually have the best chance of implementing this well, because they control everything. They control the hardware and the software, and most people probably don't run other stuff on their Macs without using Boot Camp or whatever, which is a CSM. I don't know. We'll see. As I said, they do actually have the EFI guy who invented this stuff on staff, so I'm fairly sure that all the cool stuff in the EFI spec will eventually make it into Apple's version of the firmware. So to conclude, I had a lot of fun doing this research. What measures should you actually take to thwart this kind of attack? As I said before, use an EFI password because it does prevent a lot of basic stuff. Don't let your laptop out of your sight for too long, because there's lots of nasty things that can be done to it fairly easily. What should Apple do? As I said, implement Secure Boot, as they probably have the best chance of doing it. There's a TPM on the board on this machine. It's not used for anything, so they probably should use that for key storage for EFI Secure Boot, and that would probably be tamper-proof enough to store the keys. Yep. As I said previously, they need to use the write enable pin on the firmware flash correctly. Someone at Apple told me that they actually do on later machines, so that may not be as much of a problem as I thought. They really need to audit the EFI code, because no one has, except for a couple of hackers, and they haven't done it very thoroughly. There's going to be shitloads more bugs within the EFI code, heaps more. So there's just going to be code exec bugs galore. So that's pretty much it. There's some reference material. If you're interested, I'll put these slides up online if anyone is interested in checking that stuff out. Thanks very much. Any questions? Domingo.
So, Lucas, great presentation. Thank you. From your very first example on the pre-boot environment, when getting the plain text passphrase,
yep.
From a memory allocation perspective, do you happen to store that in any memory page and then retrieve that when the exit boot services get and your code gets loaded, or you have to rely on the TCP/IP stack to send it out of the machine somewhere?
Exactly what your first suggestion was. In my example, which I didn't show you, but basically what I did was stored it in some runtime services memory. I also tried installing it in the a pointer to the physical address of that memory where it's stored in the configuration table, and then just pulling that out either at exit boot services time or even from the OS if it's in runtime services memory.
Okay, got it. Thanks.
No worries. Anyone else? Cool. Well, thank you very much for having me, everyone. Thank you very much, Louise, for inviting me.
You're going to be around?
I'm going to be around to answer any questions if you have any more questions. Thanks very much.